Hello, good afternoon, students. I am Dr. Akil Sheikh. Today we cover rank and inverse of a matrix. First of all, rank of matrix. There are two methods to find the rank of matrix. First method, a number R is said to be rank of matrix capital A if there is at least one square submatrix of A of order R whose determinant is not equals to 0, and the determinant of any square submatrix of order R plus 1 and greater than R plus 1 above should be 0. Reduce to an Echelon form, or it is called as upper triangular form by using elementary row transformations. Then the number of non-zero rows is the rank of the given matrix. Now, these are some properties of rank of matrix. Rank of AB, A and B both are matrices. So rank of product of two matrices is less than or equals to minimum of rank of A comma rank of B. Rank do not elementary transformation do not change the rank of matrix. So rank of A transpose is equals to rank of A. If A is any n by n matrix and its determinant is not equal to 0, then rank of A is n. Or we can say that if A is single non-singular matrix, then its rank is n. For any matrix A of order m by n, rank A is less than or equals to minimum of m comma n. Here m is number of rows, n is number of columns. And here this fourth property is for rank of matrix single A matrix, and first is for multiplication of two matrices. Then rank of A plus B is less than or equal to rank A plus rank B. Now here elementary transformation do not change the rank of matrix. Now next definition is here inverse of matrix. If A is any square matrix, then A inverse is equals to 1 upon determinant of A into adjoint of A. Determinant of A is not equals to 0. This is the condition for existence of inverse of matrix. Now next here we start examples. Now for example is here the rank of the matrix. This is the given matrix is. Now here we have to find the rank of the given matrix. For that purpose we have to use elementary row transformations. First of all, the first diagonal element, try to make it as 1. In given example this is the 1, so no problem. Now next the elements below this first element, making it as 0 by using elementary row transformations. Now to make second element in R2, in second row, to make first element as 0 means to make this element as 0, we have used here row transformations. Again we have to make this element as 0, so we use the combination with R1, means we use here R2 minus R1 so that this element becomes 0. Next we will use R3 minus R1, then we get next element as 0. This is R2, we operate on R2 minus R1, and R3 minus R1. In this case we see that here R2 minus R1 means 1 minus 1 0, minus 1 minus 1 minus 2, 0 minus 1 is minus 1. Then R3 minus R1 means 1 minus 1 is 0, R3 minus R1 means 1 minus 1 0, 1 minus 1 0 means. Now check here, this is the diagonal elements. This is also called as principal diagonal elements. Now it is not possible to make other elements as 0, because we will try to make this element as 0, then other elements will become non-zero. Means our target is here to make it as in terms of upper triangular form, or below the upper diagonal elements all are 0. Now in this case the number of non-zero rows is here 2. This is first row is non-zero, second row is non-zero, means all elements are not 0. So we can say that non-zero row, so we can see that rank of the given matrix is 2. So option is C option is correct. Next, given matrix, this is the given matrix, the rank of the matrix is, now the given matrix is of order 3 by 4. The order of the given matrix is here 3 by 4. Obviously rank of the given matrix is minimum of 3 comma 4, means row or column. So obviously this first option is not possible because it is maximum as compared to row and column. So remaining 3 options are here. Now here we have to use here elementary row transformations. If you observe here, this element is 4, not 1. This is 6 in second row. If we make here 6 minus 2, we get 4. Then we can easily make here R1 minus R2. So we use here this transformation. We make R2 minus R3 so that 6 minus 2 will get 4, and this 4 can easily making as 0. So we use here R2 minus R3. This operation R2 minus R3, we get these elements in second row. Now here we have to make this element as 0. Our aim is here to make this element as 0. Second, to make this element as 0. We are proceeding in first column, or we are trying to make elements 0 in first column. So we always use the combination with R1, means we operate here R2 minus R1, means we use here combination with R1. Here we have to make R3 element 0, we use combination here R3, 2 times R3 minus R1. So what happen here, R2 minus R1 means this 4 minus 4 0, this 2 minus 2 0, this 4 minus 1 3, 6 minus 3 3. We get these elements easily. Next here 2 times R3, this is R3, this is R3. So 2 times R3 means this becomes this 2 2s becomes 4, then 2 1s becomes 2, then 2 zeros becomes 0, and 2 1s 2. This is twice times R3. Now minus R1. Now elements of R1 are here. These are 4. This is 2, 1, and this is 3. Now we have to subtract these elements. Making subtraction here, this 4 minus 4 becomes 0. This 2 minus 2 becomes 0. 0 minus 1 becomes minus 1. 2 minus 3 becomes minus 1. These are 0 0 minus 1 minus 1. Next, if you observe here, these elements, these diagonal elements, now this is the next limit. These two elements become 0. Now we have to make this minus 1 as 0 element. So in this case, we have to make this element as 0. So we operate on R2. What happened here? R2 plus 3R3 means this R2 plus 3 times R3, and we operate on R3. So what happened? R2 as it is, which is here 0 0 3 and 3. These are elements of R2 plus 3R3, just multiplying to third, multiplying by 3 to R3, it becomes 0. This is 0, this is minus 3 and minus 3. So when we add, we get all elements as 0, that is 0 0 0. So in this case, the number of non-zero rows is here 2. So we can see that rank of the given matrix is 2. So option C is correct here. Next here, let A equals to, this is 2 by 2 matrix, and A inverse equals to 1 by 2 A 0 B. This is also a 2 by 2 matrix, inverse of the given matrix A. Then A plus B equals to, now here we have to find the addition of these two elements. Options are given here. Now to find the inverse of the matrix, we use here adjoint formula. Now we are given here, formula is here, A inverse equals to 1 upon determinant of A into adjoint of A. So we have to require determinant of A. We first file determinant, means this is 3 to the 6 minus 0. You will get here 6 as a determinant. Now formula is here 1 by 6 times. Now to find the inverse of 2 by 2 matrix, we just interchange these diagonal elements, interchanging its position and multiplying remaining elements by minus 1. So adjoint becomes 3 2, multiplying by minus 1 to other elements, it becomes plus 0.1. Now next here, multiplying to each term by 1 by 6. Now here this is 0.1. This 0.1 nothing but 1 upon 10 in terms of fractions is 1 upon 10. So multiplying by 1 by 6 to each element. So it is 3 by 6 means 1 by 2. This is 1 by 10 into 6, 1 by 60, 0, and 2 by 6 means 1 by 3. Now here we have to find the values of A plus B. A means here 1 by 60 and B is here 1 by 3. So directly calculating this sum. So A inverse is the given matrix. So A plus B equals to 1 by 60 plus 1 by 3, taking LCM as 60. So 60 ones are 60. So cancel, 1 ones are 1 plus this 3 to the 6, 20 into 1, 21 by 60. Now 21 by 60 is the correct answer. Which one is here? Now 21 by 60 is not given here. So simplifying this term, we know that 21 is divisible 3. So 3 7s are 21. Here 3 2s are 6. So it becomes 7 by 20. So 7 by 20 is option A. Option E is correct answer. Next, consider the matrix X whose order is here 4 by 3. Y, whose order is 4 by 3 again, and P, whose order is here 2 by 3. The order of this matrix will be, now here just observe the square bracket. First of all, we solve innermost bracket. First of all, we find the order of innermost bracket, then we find the order of its inverse, then we find the order of this whole term, then we find the order of this whole term, then lastly we find order of its transpose. Here we know that if capital A is a matrix of order suppose m by n, then its transpose gives order n by m. Its transpose gives order here n by m. It is the order of A transpose. So first of all, we have given matrix A, its order here 4 by 3. First we have to find X transpose, its order becomes 3 by 4. X transpose becomes 3 by 4 order. Then order of Y is 4 by 3. This is 4 by 3. 4 by 3 as it is. Next we have to find order of this term, X transpose Y, means multiplication of two matrices. So X transpose of Y. Now we know that here when we multiplying two matrices, then we get the order as row of first matrix and column of second matrix. If X transpose and Y are two matrices, then we get the multiplication of two matrices having order row of first matrix and column of second matrix. So order becomes 3 by 3. Next, we have to find its inverse. Inverse does not change any order. Again, we know that inverse is exists for square matrix. So order is again 3 by 3. Next, we have to find P into this term. So we first write here P. Order of P is 2 by 3. Next, P into this term. So again, we have to find order of these two matrices, P into X transpose Y complete inverse. The order of row of P is 2 and column of this matrix is 3. So order is here 2 by 3. Next, multiplying by P transpose. So order of this term is 2 by 3 into order of P transpose is 3 by 2. Now the row of first matrix is 2 and column of second matrix is 2. So order after multiplying these matrices we will get 2 by 2. Next we have to find its transpose. Again transpose of 2 by 2 matrix, again we get the same matrix 2 by 2. So option is correct. Next here, next example, the inverse of the 2 by 2 matrix 1 2 5 7 is. Now here we have to find the inverse of this matrix. Now here we have to use adjoint formula. This is the given matrix A. First we find determinant of A, means this is 7 into 1. We get 7 minus 5 to the 10, means 7 minus 10. We get here minus 3, which is not equals to 0. So inverse is exist. So formula is here A inverse equals to 1 upon determinant of A into adjoint of A. This is 1 upon minus 3 as it is. Now here we have to find the adjoint of matrix. So interchanging the diagonal elements, so interchanging 1 7, so it becomes 7 1, multiplying by minus 1 to remaining elements, it becomes minus 5 and this minus 2. then multiplying by this minus 1 to each element of the matrix, so it becomes minus 7, 2, 5 and minus 1, and this answer is nothing but option A. Next question here, the rank of the matrix M equals to, this is 3 by 3 matrix, is, now here we have to find the rank of the given matrix. First of all, to find the rank of matrix, if this first element is 1, then we can easily reduce its neighboring elements to 0, its below elements to 0. So first of all, interchanging these two rows R1 and R2, so we get 1 at first place, so R1 interchanging R2, so this matrix becomes, now here we have to make this element as 0, again this element as 0, again here we are trying to make elements of first column as 0, so making the combination with first row, so we making the combination with first row. Now here R2 minus 5 R1, that is combination with first row. Now to make this element as 0, R3 minus 3 R1, making the combination with first row, this will get here, R2 elements is here, R2 is 5, 10, 10 minus 5 R1 multiplying by 5 to R1, so we get here 5, 0, 5 is a 10, and subtracting the terms, so we get here 0, 10 and 0. This is the second row. Next R3 minus 3 R1, R3 is here 3, 6, 6, so we get here 3, 6, 6, this is R3 minus 3 R1 multiplying by 3 to R1 and subtracting, so we get here 3, 0, 3 to the 6, and subtracting these terms, we get here 3 minus 3 0, 6 minus 0 is 6, 6 minus 6 is 0. These are third row elements. Now we have to make all elements below these diagonal elements to 0, means now we have to reduce this 6 as 0. Now here we have to performing operation on second column, so we operate with second row. We observe that second row contains 0, 10, 0, third row contains 0, 6, 0. It means that when we dividing it by 10, we get here 0, 1, 0. When we dividing by 6 to third row, we get 0, 1, 0. Means we get this row, this matrix as. Then we can easily make this element 0, means R3 minus R2. We can orally find R3 minus R2, 0 minus 0, 1 minus 1, 0, this 0. We observe that these are diagonal elements, and this matrix is called as upper triangular matrix. Now it is not possible to make other elements as 0, otherwise other non-zero elements become 0. Hence here the number of non-zero rows is here 2, that is this first row, this is second row, these are non-zero rows. We can say that rank of the given matrix is 2. Rank of the given matrix is 2. And if we ask the nullity of matrix, nullity means number of rows. In this case, all 0 rows is here only 1. We can see that nullity of this given matrix is 1. Nullity is 1, rank is here 2. Next here, for which value of x will the matrix given below become singular? Now here, singular is here, determinant of A equals to 0. If determinant of A equal to 0, then we can see that matrix is singular. Otherwise, we can say that non-singular. Now, to find the value of x, first of all, here we have to find its determinant. The given matrix is here 3 by 3, 8, x, 0, 4, 0, 2, 12, 6, 0. So, for singularity of matrix, determinant of A equal to 0, we assume the determinant of A equal to 0. This is the matrix determinant in terms of determinant form. Now here, when we observe second row, it is multiple of 2. So we can 2 taking common from second row. In third row, it is multiple of 6. We can take 6 as common. So our determinant will reduces as first row as it is 8x0. Second row becomes 2 to the 4, 0, 1. Third row becomes 2, 1, 0. We take 2 as common from second row, 6 as common from third row. Then applying the procedure to solve determinant. Here 8 into, ignoring first row, first column, 8 into 0 minus 1 minus this x into, ignoring second row, first column, remaining here 2, 1, 2, 0 means 0 minus 2 plus last element here 0. Now it remains 6 into 12 and 12 is here non-zero term, dividing both sides by 12. So we get the same equation. So multiplying by minus 8, it becomes minus 8 plus minus minus plus twice x equal to 0. When we simplifying, we get x equals to 4. That is twice x equals to 8, x equals to 4. Option is here, first option, x equals to 4. Now here, multiplication of matrices E and F is G. Matrices E and G are, E matrix is given, it is 3 by 3 matrix, whose elements are cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, and matrix G is here. This is the identity matrix, 3 by 3 identity matrix. What is the matrix F? Options are given, these are 4 options. Here we have to find matrix F. We have given here multiplication of matrices E and F is G, means E into F equals to G. And what is the matrix F? Here G is identity matrix. G is nothing but here identity matrix. Now here we have to find the value of F. So we have to remove this E. So pre-multiplying on both sides by E inverse. So we get here F equals to E inverse into I. We get here E inverse into I. Again, we know that here I into any matrix, we get the same matrix. So this is equals to E inverse. It means that the value of F is nothing but E inverse. That is, we have to find the inverse of this matrix. Now here E into F equal to G. This is the given term. This is the E which is given matrix into F. G is his identity matrix. Now from this condition we get here F equals to E inverse, because this is matrix E. This is matrix identity matrix I. So pre-multiplying by E inverse we get F equals to E inverse. Now here we have to find the value of E inverse. Formula is here, adjoint method, 1 upon determinant of A into adjoint of E. First of all, here we have to find the determinant of E. This is the matrix E. Just observe the matrix here. When we are observing the matrix, there is a property of matrix. If there is a single element, with neighboring all elements are 0, means in third row it contains 0, it is also 0. So we can exclude this row and this column, and we just write its positional value, means 1 into its position value is here, its position is here on third row, third column, means 1 into minus 1 raised to the power 3 plus 3. That is, here we have to find cofactor of this one, that is 1 into minus 1 raised to power 3 plus 3 into determinant of these two matrix. We get here cos square theta minus minus plus sin square theta, sin square plus cos square is 1. So we get here determinant of E equals to 1. Here determinant of E equals to 1. I just write here directly. Now here adjoint of E. For 2 by 2 matrix we can easily find adjoint of given matrix, but for the adjoint of more than order 2, the formula is here transpose of matrix of cofactor. Transpose of matrix of cofactor is nothing but the adjoint of the matrix. Now here we have to find the cofactors of each elements. Here there is relationship between cofactor and minor. Cij equals to minus 1 raised to the power I plus j into m ij. Here I stands for row, j stands for column. This is the formula to find cofactors. Now here we have to find cofactors of each element of the given matrix. Now to find the cofactor of cos theta, so its position here first row first column. So removing first row and first column, taking determinant of remaining elements, which is here cos theta into 1 means cos theta minus 0, we get here cos theta. This cos theta is first minor. Next we have to find cofactor of this element minus sin theta. So ignoring here, so ignoring first row, second column, taking determinant of remaining elements mean sin theta in 1, which is get here sine theta minus 0. This is the minor. This is the minor. We get sine theta. And this minus 1 is here. Minus 1 raised to the power I plus j is position value, means it located at first row, second column, means I is 1 plus j is 2. 1 plus 2 is 3, means minus 1 raised to the power odd number is minus 1. So we get here minus 1. Next, we have to find the cofactor of next element. Ignoring first row, third column, taking determinant of remaining elements, which get here 0 minus 0, 0, and sign will be same again here. For this element, ignoring second row, first column. So values are here, minus sin theta into 1, which is minus sin theta. Similarly, for all terms, we can find the minors. So these are minors, and multiplying the minus with minus 1 raised to the power its position, that is I plus j, rows plus column. So we get these terms. Or simply, instead of finding minus 1 raised to the power I plus j, we can simply find first element is plus, next minus, plus, this is minus, plus, minus, plus, minus, plus, means multiplying to these elements by minus 1. Multiplying these 4 elements by minus 1, nothing but we get here cofactors. Now we have to find this transpose. This transpose nothing but changing rows into columns or column into rows. Now here we change here, it's rows here. Now here we change rows here, rows into columns. Cos theta minus sin theta 0, sin cos 0, 0, 0, 1, and this is the correct answer, and option is here C. This is the option. Next example here, if A equals to 1562 and B equals to 3784, then AB transpose is equals to, now first we write here matrix A, then B transpose, it becomes 3784. Just writing rows into columns, we get 37 first column, 84 as second column. Then multiplying these two matrices to each other, here using a row by column method, using here elementary row by column method to multiplying these matrices. Here simply multiplying first row with first column. So we multiplying here first element into this first element, we get here 3. 3 into 1 is 3 plus. Next, this second element, with second element 5 sevens are becomes 35, so it becomes 38. That is first element. Next, we multiplying first row with second column. Again, multiplying first element, this first element, 1 into 8 is here 8 plus this 5 into 4 is 20. 5 4s are 20. It becomes 28. That is second element. Next here, next multiplying second row with first column means 6 into 3, 6 3s are 18 plus this 2 into 7, 7 2s are 14, 7 2s are 14. This becomes 32. Next, similarly, multiplying second row with second column, so we have 6 into 8, it is 8 6 are 48 plus 2 into 4 means 4 2s are 8, so 48 plus 8 is here 56. So option is here 38, 28, 32, 56. Option is here A. Option A is here correct answer. Next, we have to find the inverse of the matrix. This is the complex matrix. It is 2 by 2 matrix. 3 plus 2i, I minus I, 3 minus twice I. And answer options are given. These are 4 options. Now here, to find its inverse, we have to use here adjoint formula. That is, if we take this matrix as A, this matrix as A, though matrix formula is here, A inverse equals to 1 upon determinant of A into adjoint of A into adjoint of A. This is the formula to find the inverse of matrix. Now here, first of all, you have to find the determinant of A. Adjoint of A we can find easily. That is just interchanging the diagonal elements and multiplying to this remaining diagonal elements by minus 1. So here, when we interchanging these elements, so it becomes 3 minus I, 3 plus I. This 3 minus I, 3 plus 2I, 3 minus I, 3 minus plus 2I means option B or option D may be answer. Multiplying to remaining elements by minus 1, it becomes minus I, this becomes I. Now here we have to check the value of determinant of A, which is either it may be a 12 or maybe a 14. For that purpose, we have to find the determinant of A. Now here, to find determinant of the matrix, method is same here. First multiplying these two elements, that is principal diagonal elements. Here this becomes 3 plus 2i into 3 minus 2i minus this minus I into I into I becomes I square. This minus becomes plus, or we are just right here, minus I into I becomes minus I into square. Now simplifying this term, here these two brackets in terms of a plus b, a minus b form. We can use here a plus b into a minus b, a square minus b square. So here 3 is nothing but a and twice I nothing but b. It becomes a square minus b square, means it becomes 3 square minus b square, means twice I square, that is it becomes 4 I square. Then this is minus minus plus, I square is minus 1, it becomes minus 1. Now 3 square is 9, this I square is minus 1, minus minus plus 1, it becomes 4, and this is minus 1. So this equals to, we get here 12. 9 plus 4 is 13, minus 1 is 12. So this is here A inverse equals to 1 upon determinant of A into adjoint of A. So we find the value of determinant of A, which is 12 here. So adjoint of A is here. Simply interchanging the principal diagonal elements and multiplying remaining elements by minus 1. That is, if A equals to, this is the matrix A, B, C and D. I am talking about only for 2 by 2 matrix. To find the adjoint of more than 2 by 2 matrix, we have to use here transpose of matrix of cofactors. So in this case, adjoint of A, adjoint of A is nothing but as interchanging these principal diagonal elements. We get here D, this is A, and multiplying remaining elements by minus 1, it becomes minus B, and this is minus C. This is the adjoint of A. In this case, we cover most of the examples which has been asked in previous GATE examinations, depending on rank of matrix and inverse of matrix. In this case, to find the rank of matrix, here we use here second method, that is reduce the given matrix to an upper triangular form by using elementary row transformations, and then the number of non-zero rows is called the rank of the matrix. This is the result. So thank you, class.